we talk about uh, the forces involved in dragging various cars of a train. So if you see the picture here, so here we have a very simplified model of an engine that's here, that's pulling three cars, A, B, and C. So um, so each of these cars is assumed to be able to move freely on the rails. Okay? There is no impediment to their motion. So the frictional forces essentially that are encountered are negligible in comparison to these forces. Right? So that's the assumption. So anybody who has seen a train would know that there's a locomotive that pulls these cars. And these cars are linked together by a chain of some sort. Okay. So the question is, what is the tension in these two chains? Okay. Given that there is a force being applied by the engine on the very first car. So that's the question. So let's take a look at the free body diagrams. So if you look at car number C, it's being pulled forward by a force equal to T2, right? And so by Newton's third law, so every action has an equal and opposite reaction. So therefore, the the car B, is essentially being dragged backwards. That's restrained by force equal to T2, and it's pulled forward by force equal to T1 here. Okay. In the same way, if you look at the free body diagram for car A, we see that it's being pulled back or held back or restrained by a force equal to T1, and it's being pulled forward by a force equal to F. Right? So, so all this assumes here that these chains themselves are taut. Okay, and that may not necessarily happen when the train is just starting out. See, what trains generally tend to do is that when the train stops, right, when the engine stops, then these carriages they move forward a little bit, okay, and they come to rest. So at the very beginning, okay, so these chains of the motion, these chains are not taut. So what happens here is that when the engine starts up, and it moves forward, it just has to pull the first car to begin with. Okay, and then uh, what happens here is that this chain that was slack before becomes taut, and then therefore this also starts to affect the motion of the entire train, and soon afterwards this chain also becomes taut. So all these cars and the locomotive are moving in tandem. Okay, so that's what happens in the very beginning. So here we assume that all the cars A, B, and C are moving in tandem with the locomotive. Okay, so that's the assumption. So we also assume that the mass of C equals mass of B equals mass of A equal to m. So so what we do here is we write the Newton's laws for car A. So we get F minus T1 is the net force equal to mass times acceleration of A. Now the accelerations of all three cars are the same because they are well connected with each other and these strings are all taut. So the length moved by A equal to length moved by B equals length moved by C, and therefore their derivatives with respect to time, that is the velocity and accelerations, are also the same. So, so f minus t1 equals m times a. So here if we look at car B, so it's t1 minus t2 equals m times a, okay, and then for C, t2 equals m times a. So what we do here is that in order to solve for this, we add up all three of these equations. So the t1s just cancel out, the t2s cancel out. We get F equals 3 times mass times acceleration, right? So the acceleration is equal to F divided by 3m. So this whole thing behaves, this whole system here behaves as though we have a mass of 3m being dragged by an engine. That's essentially how this thing behaves, right? So for the purposes of motion, okay, we could replace this three car system by a one car with mass equal to equivalent mass equal to 3m. So we could do that. So nevertheless, okay, so if you look at the tension in string 2, so essentially the tension in string 2 is T2, it is m times F divided by 3m, so it's F by 3, and so T1 equals ma plus T2, so it's F by 3 plus F by 3 is 2F by 3, okay. So what happens here is that uh, so in here the we know that this force is F, okay, so we can write this T0 equals F, right? So what we see here is that the tension in this string is in this chain is the highest, in this chain it is lower, and in this chain it is the lowest, okay. So essentially the chain that goes between the first car behind the engine and the engine itself needs to be the strongest, okay. So if all three cars have the same mass, okay, and so if we also know that the acceleration here, okay, is some value, okay, so the tension here, okay, equals, okay, whatever uh, mass is behind that chain, right, times a, right. So uh, if the mass is 2m here, okay, and the acceleration is F divided by 3m, so this tension equals 2F divided by 3, okay. So that's the rule of thumb. So if you look at here, so the mass behind, okay, is only m, so m times F divided by 3m, so we get only F divided by 3, okay. So that's the way to take a look at this problem. uh, so the crucial thing to understand is that these forces in the chains are also contact forces, okay? You could solve contact problems the very same way, in which we just solve this kind of stuff, okay? So I hope this helps to better understand how contact problems need to be addressed and solved, and it'll help you to better conceptualize the problem, okay? So if you like this video, please press the like button and subscribe to this channel. Thank you.